Welcome back. We're going to continue the second section. So the next speaker is Dr. Guillaume Jubeaux, and he's an ecotoxicologist. So we saw in the previous presentation that there are many chemicals and that analyze them by chemistry might be tricky. So one of the solutions is to use biota, because they are exposed to the environment and they are integrative. So that's what Guillaume Jubeaux will present us. He's working in a private company called Biomae, which use gammarus to do environmental diagnostic. So please.
Good morning. My name is Guillaume. I'm glad today to show you some development and large-scale deployment of a new solution of biomonitoring to assess contamination and toxicity in aquatic environments. So to introduce my presentation, I show you the 9 planetary boundaries that you know. And one of these, for novel entities linked to chemical pollution, has been already exceeded. So you can see on the right a picture that shows the continuously increasing of chemical production in the world, with a strong diversity of substance, newly with perfluorinated compounds, microplastics, for example. So in this context, and especially in Europe, there is a strong regulation about the assessment of water quality. It is the Water Framework Directive. This Water Framework Directive puts a strategy for monitoring chemical status with a goal is remove priority hazardous substance in water, and a second strategy around ecological status with a goal is preserve, restore aquatic biodiversity. So here on these two pictures, you can see a result of quality states in France during the last years. In terms of monitoring strategy to assess chemical and ecological status, there is 2 main methodology. First methodology for chemical status is the monitoring by water. You take sample of water and you measure concentration of substance. The second strategy is the monitoring of the presence and the abundance of communities, the species present in each communities, including flora and fauna. So today there is some needs to be able to link chemical results and ecological results, because it's difficult to link these both status. Why? First, on chemical status, there is some problem on monitoring water, because there is some problem about the representativity of punctual sample. When we measure in water, we do a punctual sample, so it's not really representative of level of contamination in waters. Second problem is the biodisponibility, because bioavailability, sorry, because when you measure in water, you don't take the part of contaminants which able to enter in organism. And it is this fraction which is potentially toxic for organisms. So to take organisms, it's more relevant. Third, what we do for hydrophobic substance, because some substance like perfluorinated compounds accumulated preferentially in biota than in water. So it's another problem. At the other hand, for ecological status, there is some confounding factors which may explain an impact of biodiversity other than chemical pressure. You can have, for example, habitat effect, predation, competition between species, and availability of food resources. So, in this context, ecotoxicology is proposed to improve the link between chemical status and ecological status by understanding the fate and impact of chemicals on biota, and more especially on individual effects to link to exposure and effect on communities. So it exists different biomonitoring approach for ecotoxicology. First, you have passive monitoring. The principle is to sample native organisms on the station and to do some measure. Another and new approach is active monitoring, and it's based on the caging of control organisms. You produce your organism and you expose them on the station. The advantage of active monitoring compared to passive monitoring is, one, it's applicable everywhere, compared to passive monitoring, where you can use this methodology only if a species is present on the station. Another advantage is, with active monitoring, you'll be able to produce organisms from a reference population and to do and to realize spatial comparison. Because when you use native organisms, there is some difference of sensitivity in population, and you can compare each station. Another advantage is the possibility to more calibrate your assay organism by sorting by size, gender, status reproductive, and you have more relevant response. But take care and have some precaution, because if you do active monitoring, you need to using non-invasive species to avoid the dissemination of invasive species. So in Biomae, we choose a small amphipod crustacean, which is named Gammarus fossarum, which is introduced in a European technical report for active biomonitoring. So there is different species, but this species is interesting because it's a non-invasive species in Europe and largely used, and largely present. It's a well species adapted for caging. It's not the case for each species. And it's easy to handle, for example. So, in this context, during 15 years, in a French research institute in Rai, there is development to propose in situ bioassay by caging gammarids to assess contamination and toxicity. So there is many publication and thesis. After this development, there is a technology transfer in a private laboratory, Biomae, which is created in 2014. We have raised funds in 2015 in order to develop large-scale pilot in France and to industrialize this methodology, because when INRAE deployed this method, it was up to 100 stations, and today we deploy more than 1,000 stations per year. So there is some work to industrialize this research tool. In 2018, we enter in regulatory deployment in France in response to the new obligation of the Water Framework Directive, which imposed to measure some chemical substance in biota. In 2019, we have the first standard publication in France with AFNOR, and we continue to produce a free standard around toxicity measurement. Some number in 2022 we realized a 2 million turnover, and in Biomae we are around 30 collaborators. And since our creation, we have realized more than 7,000 bioassays in France, Luxembourg, and Switzerland. So, our protocol. There is different steps. The first step is the breeding of gammarus. So, we have some breeding ponds where we produce the small crustacean. After, we have a step to acclimate the organism under controlled laboratory condition, and we sort organisms according to their size, gender, etc. After the organisms were sent to the station, and the organisms are exposed during 21 days continuously in the river. So you can see we put the cage in exposure systems. And after, organisms were exposed in a realistic condition during 3 weeks. After exposure, the organism sorry. The organism come to the laboratory where they are sampled, and we do different analyses to measure contamination and some biological response to measure the toxic impact. So, with this method, there is 3 main applications. The first application is to check the compliance with environmental quality standards in biota, EQS, for 15 priority hazardous substances in response to the Water Framework Directive. The second application is to assess the level of bioavailable contamination for 100 substances. And for this, in RAE, we have developed some contamination and toxicity thresholds to interpret the result. So you have some threshold for metals, pH, PCB, chlorinated, brominated, perfluorinated compounds, drugs, pesticides, cosmetics. And third application is to assess the toxic impact with cocktail effects of micropollutants in aquatic environments. So first application, you have here an example, an illustration of the compliance of benzoapyrene at large scale in France. And you see there is some station which is downgrading. In complement, there is some EQS defined in fish. Sorry. There is some EQS defined in fish, and for this, in France, has been developed translation between gammarus concentration, which is measured, and fish concentration to check the compliance with EQS in fish. And here you have an example for perfluorinated compounds And we can see that there is more downgrading compared to benzoapyrene. Second application is for assess the level of contamination with our threshold. Sorry. Okay. Here, it's our methodology, which is defined in some publication by INRAE. We have defined a contamination scale coming from large-scale development in France. And with this database and statistical approach, we have defined a contamination scale to assess the station in France. So I give you some example. In the south of France, for example, for cadmium, you can see there is different hotspots. Hotspot which is linked with industrial discharge. And we can have also some hotspots which is linked with geochemical backgrounds, especially for metals. You have another example with a PCB, where you can see that there is a strong contamination on the road, and it is an historical contamination of this area that you can see clearly on this picture. Other example, in the north of France, for lead, for example, where you can see some hotspots, which is mainly linked with all metal works. And on the right, you can see for difluphenican, which is a weed killer, mainly used for agriculture or in cities. And you can see there is a strong occurrence of these molecules in the north of the watershed. Oula. Third application, we have the same approach for contamination by the fact we define a toxicity scale to be able to assess the level of toxicity. I present you two markers. The first marker is the feeding inhibition. And for this, we use a food substrate, which is consumed by organisms during exposure. And after exposure, we measure the rate of consumption by organism. The second marker is reprotoxicity. We count the number of embryos after exposure. So these two markers are more non-specific or global marker of toxicity. And I have some example. It's an example in the south of France. On this picture, you can see that there is many campaigns that have been realized, and this is the result for feeding inhibition. So you can see that we can define reference station, and we are be able to ranking of station, and especially to identify hotspots. When we add a second marker, reprotoxicity, the interest is the weight of evidence, because we are able to confirm the reference station and identify the main hotspot, which is impact both on feeding inhibition activity and reprotoxicity. So in conclusion, gamma-rate caging is an available, standardized, and routinely deployed method. And we are under work to propose an international standardization at ISO. So this method is applicable on a large scale, but also for more locally study, for impact study, for industrial discharge, urban waste, wastewater treatment plant. And here it is an example for a watershed survey where you can see with the red ring, we have identified the main source of toxicity on the watershed. Thank you for your attention.
Thank you, Guillaume, to be perfectly on time and to show what you're doing in your... Is it a startup or is it...
Yes, it's a startup, and the last 2 years we have joined a group in France, which named Groupe Carso, which is a leader in analytics.
So a future of PhD students can move to the, to the industry and have a nice work there. Is there questions?
Thank you. Thank you. Yes, you hear me? Yes. Thank you for this presentation. I have a question. If I well understood, you expose the gamma during 20 weeks in a river, for example? 21 days, 21 I would say. Sorry. And then you collect the gamma and analyze them.
Yes.
So I understand relatively well that you can see the effect of different contaminants on gamma, but I don't understand how you can say the level of contamination of the river with gamma, because how you can say that 100% of contaminants present in river are accumulated, thank you, accumulated in gamma. How you can say that?
We mainly quantitate hydrophobic substance. It's your question?
Not only hydrophobic, but all kind of contaminants. You talk about metals, you talk about pesticides, you talk about pharmaceuticals. Yes. So in this kind of contaminants, you have hydrophobic, hydrophilic, different kind of chemicals.
Yes. For example, we didn't find glyphosate in gammarids because it's hydrophile. We have tested some strong concentration and there is no accumulation with a limit of quantification which are able today. But the main group of substance that we can measure is metals and PCB, PFOS, PFAS, each this molecule. It's more difficult, for example, for herbicides, but we have some molecules which have log de KOW strong and which well accumulated in gammarids. So, in fact, gammarids is not the solution, but it's complementary to water sample, for example, to search hydrophile substance like drugs, because we try to search some substance like ibuprofen, paracetamol, and we didn't find in gammarids because it's difficult to accumulate. But for medicament, for example, we have some molecules like carbamazepine, which well accumulated in gamma. So we try to integrate a large group of molecules to detect which molecules are relevant with gammarids. You know.
Sorry, allow me to complete the question. In fact, I understand that hydrophobic compounds are easily absorbed. But in the case of great amount of particulate organic matter, which could retain this hydrophobic compound, I suppose bioavailability is reduced. Is it working in this case? Or you can have a bias in this case?
Yes, there is it's the importance of bioavailability, which may be influenced by organic matter, for example. But it's during exposure, organisms for bioaccumulation assay are not feeding, so they hit the organic matter which pass in the river and contaminate and are contaminated by the food resource present on the station. So it's not only a contamination by water; it's a contamination by food.
Thank you. Do you have other questions?
Thank you for your presentation. My question is more about the future. You create this startup based on your research, let's say, and yeah, you are monitoring now aquatic areas. In the future, you want to integrate this to probably a next step where you want to remediate or fix the problem, or how you can see the future of your startup?
We are not a laboratory which gives some solution to remediation. We are an analytical laboratory which are able to identify hotspots and to identify the source of contamination. And for example, we work well with a water agency, and they use this result to make remediation program on their country, you know, by built wastewater treatment plant, or to make some changement on agriculture. So it's a tools to aid to take the decision, you know, but we don't give some advice for remediation.
Other questions?
Thank you very much for the presentation. Maybe I missed this information, but are you using in other organisms or just this?
Just gammarus.
Okay, but are you planning to add somebody else?
Yes, which is seen with our result. For example, in some contexts with strong contamination by herbicides, we have seen that gammarus are not very sensitive to this substance. And today we would to develop some bioassay with a vegetal, with a plant, because it could be very complementary to have a flora and fauna model organism.
Yes, okay, so thank you again. We can applause again.